Continuing our discussion with animation, last time I talked about key techniques such as keyframing, kinematics, and dynamics, and I alluded to something called articulated figures that was used in kinematics and dynamics. And if you can remember, it's basically just a skeletal structure that represents the bones of a model. Now, I didn't go into too much more detail than that, and that's what I'll be doing with this presentation, talking about techniques called skinning and rigging, or actually reverse that, rigging and skinning. So what is rigging? Rigging is the process of creating the skeletal structure hierarchy and rendering this skeletal structure. So what you'll see on the screen, this is an example of a skeletal structure hierarchy. You'll have your root, and then I'm not sure. I'm sure the root is generally your center of gravity. A lot of models choose the hip instead of an arbitrary root as the center of gravity, the hip or pelvis, because the pelvis and the hip are generally located around the center of gravity, and then everything else kind of um, inherits from that. So connected to the pelvis, you have the left hip and the right hip, and connected to the left hip and the right hip, you have the left knee and the right knee, and so on. And so, by association, the ankle is connected to the pelvis through the knee and the hip. Now, this isn't too terribly complex, but they can get a lot more complex depending on what you're trying to animate and how high def you want your animations to be, or not really high def, but how realistic you want them to be. And getting your hierarchy right is the first step of having a more realistic animation, and it's a big part of rigging and um, I'm sorry, I just went blank for a second. It's a big part of it's one of the biggest parts of rigging, and without the skeletal hierarchy, you can't really go forward. Um, But rigging on its own, it's you're creating a skeletal structure. It could be complex. It could just be a simple stick figure that goes inside your model. And generally, it's done by hand to ensure accuracy and precision. And that's a very painstakingly long process. But for the high quality animations we're used to seeing, especially in video features or in movies, it's usually done by hand because there's no processes at the current point in time that can successfully automate the rigging process for a model to such high degree or to such high resolution uh, and accuracy that hand modeling can be. So just like how we probably are hand modeling um, our scenes for our programs, you're going to be doing the same thing with the bones and the skeletal structure, which for small scenes isn't that crazy, but um, an interesting statistic I got from reading a journal article is the line Aslan from the Chronicles of Narnia took that team 5 months to rig just his face, just the components for his face. And facial rigging tends to be a little more complex than just rigging a normal body because there's a lot of nuances that come with the features and shapes and poses of a face. But if I recall correctly, the face of that model of Aslan had over 700 individual bones or components in it. So that can give you an idea how complex it can be, and it's hard to automate something like that when you need the precision of experienced animator. So once you have the rigging done, you have your skeletal structure. And I should mention in OpenGL and C++, this is represented as a struct, very similarly to how a linked list, contains data and a pointer to the next linked list. The struct for a bone, for instance, or the struct for a joint will contain a coordinate and then a reference or a pointer to the next joint. So what can happen is it can quote unquote draw a line representing the bone to the next joint. And in rigging processes, most mm, in implementation, it's usually represented by joints only because it reduces redundancy to have to define multiple bones with the same joints, and it gives you and the joints of the skeletal structure are more of what dictates the animation. The bones are nothing without the joints, so I think it makes a little more sense to just um, compose your skeletal structure of joints. And in case I wasn't very clear, you create a strut with the coordinate of a joint and then a pointer leading to the next joint. And that list, that hierarchy of joints is going to become your hierarchical structure or the basis of it. Now, once you actually have your skeletal structure, that's when the skinning portion of the process comes in. Now, skinning is not as gross as it sounds. It's simply just merging the rigging to your 3D mesh or your model. So, think back to your 3D models that we've done in our programs. Every single vertex, every single one that we, created needs to be bound to our skeletal structure. So that we only have to worry about moving our simplified skeletal structure with a lot less vertices, because the detail of it is not as important as the aesthetic detail needed for a 3D mesh. And skinning is the process of binding each and every one of those vertex to a joint or bone, such that whenever the bone moves, via the joint, there's a function that calculates how the mesh will move with that, how it will transform with it. And that's what skinning is. It's the process of merging them. And there's quite a bit of skinning techniques, but I've kind of gone over what skinning actually is, and that's pretty much what it is. Each vertex bone pair is assigned a weight dictating how much the mesh will move when the bone is moved. And this is actually usually accomplished in implementation with transformation matrices, successfully associating one bone to many vertices with unique weights. And in this way, you can animate a very complex polygonal model by only shifting the coordinates of a skeletal structure, which will have an extraordinarily lesser amount of vertices. Now, skinning, it kind of sounds simple. You just assign a vertex to a joint or a bone, but it's not quite that simple, because you get visual artifacts when you just have one weight for each vertex. To achieve a realistic human motion is quite a hard task to accomplish, and without an incredible time spent tweaking individual skinning weights, just animating your skeleton in tiny different poses to see how it affects your mesh, and tweaking very, very small numbers for the angles of the joints, and spending a ton of time doing it. Yeah, if you have all the time in the world, you will probably get a better looking animation than someone using a method to speed it up. But again, time is a very valuable resource, and not everyone has enough time to do that. A very popular method that was introduced in 2002 via a scholarly research paper by a young gentleman with the last name of Wong is called multi-weight enveloping. Now, it's a kind of a complex process, but what it entails is the transformation matrix of each bone that we alluded to earlier is combined with the inverse rest transformation and the weight to produce a weight matrix that gives each vertex 12 weights to influence each bone. Now, that's a little complex when you're hearing, but what that means is instead of just linear, it's still a linear process, but we're just doing it a lot more times. We're scaling it up by 12, but instead of just having one linear connection from each vertex to each joint or bone, that whenever this bone moves in this direction, 100% of that vertex is moving in this direction, not necessarily the same direction as the bone, but whatever the function calculates that mesh to move according to how the bone moves. What multi-weight enveloping does, it associates 12 weights to the vertex. So what that means is, however a bone chooses to move, there's a certain weight um, associated to the vertex. So like 20% of it will move in this direction, or it's 20% of the force will cause it to move in this direction, and 2% of the force will cause it to move in this direction, and you can get a lot more accurate and precise that way. And it's actually pretty necessary to avoid some visual artifacts, um, like volume loss artifacts. I've kind of forgotten to go with my pictures here, but this is what this is your skeletal structure that we've made, and skinning is just the act of putting these together and making them, giving them a relationship that's meaningful, such that you can animate only the structure without having to worry about every single vertice of this complex, detailed surface model. And this is the visual artifacts I was talking to right before I decided to remember that I had pictures to show. As you see here, when the knee bends, it kind of flattens out and becomes very sharp, and it almost looks like a big part of the shin here is going inside the thigh here, and that's because there's not enough detail in the weights that dictate how the mesh is going to move based on the joint movement. And multi-weight enveloping kind of fixes that problem, and allowing it allows stricter weights to make sure that it doesn't deform in such a way that it looks very unrealistic. And another extension, it can be thought of as another method, because it can be used just with straight up skinning. And you might hear, like, I call it straight up skinning because it's the most basic method of skinning. But you might hear it referred to as linear blending skinning, or linear blend skinning, or skeletal subspace deformation. And whenever I say base skinning method, that's kind of what I'm referring to, where you attach a weight from one vertex to one joint or bone. But another extension to any method is an example-based method. So what this entails is you do a little extra model work to avoid having to do the tedious task of finding appropriate weights for each of your vertices. So it kind of uses keyframing. That you have over here our input polygon meshes, and we have various poses for it, right? And what the algorithm for this does, example-based skinning, is it applies weights to each vertex such that it fits the position of each example pose. So in this case, we have 4 example poses, and we're gonna the data for the weights of the vertices will manipulate such that this skeletal the skeletal structure will conform to this pose, and this is what the skeletal structure will look like inside. And then we'll do it for this one and this one and this one, and we'll compute all those weights together, and we'll find that we'll find the kind of like the average. You can't really just average them together, but you use that data. And once you find the best fits, you keep those weights for your vertices, for your structure. And it's really interesting that if those weights work for this model or this model, it turns out you probably don't even have to do these, because if you use the weight that works for this one and you attempt to animate to a model that looks like this, it'll work and it'll look good. So it's kind of the thought that if you can find correct weights for one pose, and it looks good, and you can correctly animate that pose into another pose, then you're going to be able to correctly animate that pose in any other pose, and your weighting task is pretty much finished at that point. And I think that's pretty cool. So I mean, I kind of just scratched the surface. There's as far as rigging goes, the manually rigging skeletal structures is still very commonplace. There's some there's a lot of methods and algorithms in development for. Well, there's some out there that are quote unquote accepted for automation of a rigging structure, but they're very imprecise, and they the scope of their use is not much more than low quality detail animations, and you'll it's just not feasible at the current moment to use in a big scale procedures such as a Pixar movie. Um, I did read it. I did do a previous paper on a journal article with a rigging method that will take the rig of a model that's already been made and be able to transfer that rig through various steps and deformations. Be able to transfer that rig into another model, and it doesn't. The models need to be sort of similar, but you can take the skeletal structure, the rigging of a horse, and turn it into the rigging for a camel, or you can take a rigging for a cat and turn it into a rigging for like what did they do? I think they went from cat to giraffe is what they went to, and it worked pretty well. Of course, none of the detail or none of the models and detail and structures were so complex, but for lower count vertice or lower count joint structures, it works pretty well, and um, that may well be the best quote unquote automation technique for rigging because it's not quite pure automation. You have to have something to work with before. You have to have someone model that structure before, so somewhere down the road, someone is doing that really hard work. But I saw a lot of papers for rigging and skinning methods. More with skinning methods. Skinning seems to be a really popular subject right now in 3D computer animation, and it was actually very hard to research because it, when you put skinning algorithms or rigging algorithms in Google, the first thing you see is not Wikipedia anymore, or it's not even on the front page, and you're linked to journal articles and graduate level course PowerPoint presentations, and it's really hard to find the information that's useful for me without it all going over my head. Um, but yeah, I hope that gives you the general gist of what skinning and or rigging and skinning is, and its importance in the role of 3D computer animation.